Yeah. So we are very pleased to have Alicia Carriquiry with us to give a lecture today for our AI seminar series. So Alicia has been on the faculty in the Department of Statistics since 1990. Currently, she's distinguished professor of LOS and president's chair in statistics, and also the director of the Center for Statistics and Applications in Forensic Evidence, a National Institute of Standards and Technology Center of Excellence. Her research interests include measurement error modeling, survey sampling, and biasing method. In recent years, she also got interested in machine learning algorithms and applications in different disciplines, in particular in forensic science. She has published 150 peer-reviewed journals and has mentored the work of 20 doctoral students and 5 postdoc researchers. Today, she's going to talk about machine learning in forensic applications. Alicia, please.
Thank you, Hailiang.
Yeah, welcome.
So this is going to be mostly to introduce you guys, the audience, to some of the problems we're working on. So I don't pretend to show you solutions to anything, just to describe some of the problems we have here. And I always like to start with this one story because motivating. This gentleman here is called Keith Harward. And Keith Harward used to be a sailor back in the 1970s or so, 1980s, early 80s. He was stationed in Norfolk News in Virginia. His ship was anchored there. And during that time, somebody that was wearing a sailor's uniform committed this horrendous crime. Somebody went into a home, raped the wife, and killed the husband. And in the process of raping the wife, bit her in the leg. And it was horrible. The investigation went on and on and on. They couldn't find a suspect. Long story short, because of some unrelated issues, Keith Harward was accused of committing the murder. Not only was he accused of committing the murder, he was tried and found guilty, in spite of the fact that the wife said that he looked nothing like the person that had assaulted her and killed her husband. But the evidence that was presented by a forensic odontologist turned out to win the day, and the juries. And what the evidence was this bite mark evidence. So a couple of forensic odontologists testified that that the dentition marks that were found on the leg of the woman matched Mr. Keith's teeth to a degree of scientific certainty, whatever that may be. Nobody other than Mr. Harward could have left those teeth marks. And lo and behold, he found himself in jail. He was incarcerated for 36 years. For 36 years for a crime he really hadn't committed. He was released about 6 years ago now, thanks to the Innocence Project lawyers who had some DNA that was found at the crime of the scene analyzed. When Mr. Harward was incarcerated, DNA analysis was not commonplace. All right, so that I hope serves as motivation for the type of work we do at CSAFE. So let me move on. So as it so happens, I think most everybody except for some forensic, some forensic odontologists will agree that what's called forensic bite mark analysis is pretty junky. I mean, it's what people would call junk science. So what do we mean by junk science? Well, for example, whether results obtained by one forensic odontologist might be reproducible. So if you show the same images of abrasion injuries to more than one person, will they come back and agree on the conclusion? And, you know, there had been no studies until very recently about this type of evidence. And so a pair of forensic ontologists took it upon themselves to see whether they could, figure out whether there was some reproducibility in this visual inspection of abrasion injuries. So what they did is they took about 80 some images of injuries from actual cases and presented these to volunteers. So there were about 40 forensic odontologists that volunteered to participate in the study. And what they were asked was to look at this 80 abrasions, so this 80 injuries, images of injuries, and classify them into, for sure, it's a human bite. It could be a human bite, but I'm not sure. It's an animal bite, or I don't have a clue. And the hope was that most of them would agree on those assessments. And so what I'm going to show, this plot that I'm showing you is a little busy, but allow me to explain. So each row here represents one of those 80 some images of bite marks, of injuries. And then the colors here reflect the conclusion. So the green is, I'm not sure, the dark green. The light green is not a human bite mark, but a bite mark. The dark blue is, I think it's a human bite mark. And the light blue is, for sure, it's a human bite mark. And what you would hope, of course, is that all of these rows are of a single color, because that would mean that every odontologist would have agreed on what that image represented. It turns out that, as you can see from this plot, agreement was not existent except for a few of the samples on the top and a few of the samples on the bottom, and that's about it. In spite of this, this is still being admitted in court. Precedence in the criminal justice system is almost everything. And so the Innocence Project keeps finding people that have been wrongly accused because of this type of evidence. Now, is that the exception or is it the rule? And in terms of science, and it turns out that that's forensic bite mark analysis in terms of lack of scientific backing, lack of reasonable studies, completely ad hoc type of quote unquote science is not the exception. Rather, it's more or less the rule. And this was the topic or the findings of this panel that that was organized by the National Research Council, and that in 2009 published this one report that was pretty path-breaking. That what they did is they went and they looked at just about every forensic discipline and looked at what the literature was, what the science was behind it, whether there were well estimated error rates, and so on and so forth. And what they found was that most forensic disciplines stand on pretty shaky science. And the worst culprits was what is called the pattern comparison disciplines. And those, unfortunately, include many of the things that have a reputation, have a good reputation, like latent prints, like fingerprint analysis or ballistics, or shoe and tire treads, or bloodstain patterns, handwriting analysis, and of course, our good friend, the bite marks. And so what happened was that in 2014, the Obama administration, and there were many scandals that were associated to faulty forensic analysis. And so in 2014, the Obama administration made some money available for a research center in forensic sciences, and we competed and received the funding. So that was 7 years ago. We got renewed for 5 additional years last year. So CSAFE is now on its 7th year of operation. So what's the question of interest? So the big question in forensic in forensic testimony is what's called the question of source. So if you find a shoe print like this one that I'm showing you on top here at a crime scene, you have a defendant, and this is the defendant's shoe, let's say. Can you say that these two images, that this particular print was made by this particular shoe? And so this is the typical question. If I have two items, can I say they have a common source? So if I find a menacing handwritten note, and then I have a large number of samples of handwriting from the defendant, can I say whether it was the defendant who wrote that particular note? And so this turns out to be a difficult question for many reasons, in particular because you end up comparing a smudgy. What you want to do at the end of the day is find some way to quantify the similarity between, let's say, this smudgy print up here and this much better print of the putative shoe over there, and that can get really tricky. So before I go there, then let me formalize the source problem from a better, more statistical approach, if you will. So in court, typically you have two competing hypotheses, what we call the the prosecutor's hypothesis, which is the defendant is the source of the evidence. And then what we might call the defense's hypothesis, which is somebody else was the source of the evidence. This is an old problem, and this has been around for a long time. And the first person, perhaps, to, or at least the first person to come up with a principled approach to answering this question was Dennis Lindley, who in 1977 published this really excellent short paper in Biometrica, where he actually tried to come up with an approach to addressing this hypothesis question. And so if you haven't read this paper and you're a statistician, I suggest you do, because it's really very nice. So what it's pretty basic. So what Lindley said is the following. He said, suppose that I have measurements from the item at a crime scene. Let's say I have M measurements from the item at a crime scene. I compute the mean, and I hypothesize that X bar, the mean, has a distribution with some unknown mean theta 1 and some variance sigma squared over M. And then I also have measurements, let's say N, from the item I recover from the suspect or the defendant, and call the mean, let's say it's Y bar, and that comes from, it's generated, it has a distribution with some unknown mean theta 2. And the same variance, sigma squared, but divided by N. So the prosecutor's hypothesis in this setting is, or the source question in the setting is equivalent to testing a hypothesis of equal means theta 1 equals theta 2 versus different means theta 1 different from theta 2. And so when would you think you have evidence of in favor of the prosecution? Well, you would have evidence. This is where Lindley came up with something that was really novel at the time. He said, you need two things in order for the evidence to favor the prosecution. Obviously, you need the two means to be similar, sufficiently similar, right? To say maybe they were generated from a distribution with the same mean. But you also need another thing, which is the matching values need to be rare, because if both X bar, if all the X measurements and the Y measurements are commonly observed values, then the fact that Y bar and X bar are non-distinguishable doesn't tell you much. But if they are rare, then you're onto something. If observing that degree of similarity is rare, then you're onto something. And what what Lindley said, he said, all right, how are we going to determine how are we going to combine these two things into some sort of a statistic? He said, well, let's assume first that theta 1, theta 2 have come from a common distribution with mean mu and some between source variance tau square. And what he did then is he came up with this likelihood ratio statistic, which essentially is tells you what the odds of in favor of same source are given the data you have observed. Given conditional on the two hypotheses. So the numerator here is the probability of observing what you have observed. So essentially the probability of observing the evidence that you have observed, the degree of similarity, if the prosecutor is right versus the probability of observing the degree of similarity you have observed if the defense is right. So the denominator here is the, if you will, the coincidental match probability or a probability of that you would observe a high degree of similarity only by chance alone, essentially. So in those days in 77, there were no big computers and there was no Markov chain Monte Carlo methods. And so what Lindley did is he made a million assumptions, but he did derive expressions for the numerator and the denominator after many simplifications, but nonetheless, the results were very revealing. So the numerator, of course, is just if the prosecution is right, then both X bar and Y bar come from a distribution with a common mean theta, and so he is just averaging overall possible values of theta here, being a good Bayesian that he was. In the denominator, of course, you can assume independence, and so this would be the expression for the denominator, and he came up with an expression for this ratio that's kind of very intuitive. So it turns out that this ratio was a function of the product of two terms. The first term is this squared difference between X bar and Y bar, and that has to do with the similarity. How much do these, how similar are these two sample means? The second one had to do with the rarity, and this Z here is the weighted average of X. It's a function of the weighted average of X bar and Y bar. And so what you're looking at is to see how far away the average of these two things is from the mu. Remember, mu was the overall mean, the mean of the generating distribution of theta 1 and theta 2. And so this squared difference has to do with rarity. And so so as a consequence, then what he said is, one should use this likelihood ratio statistic as a measure of the strength of the evidence. It measures both the closeness or the similarity and the rarity, and that's what you want. So it's a one number summary of the strength of the evidence. All right. So the problem is, Dennis Lindley illustrated this using an example from glass. I believe he used refractive index of glass for his example. And so something that's numeric, and he could make assumptions about the form of the distribution of the numerator and the denominator and so on and so forth. What happens though when the data that you're working with are in the form of images? And that's where I'm going to go next. So when data are images, of course, life gets a little complicated and so this is the type of data that I'm talking about. Here we have a sample of handwriting. Here we have, you saw this already. So here's a crime scene print of a shoe. Here's the defendant's shoe. Here is a land. So this is a portion of the surface of a bullet. And in the bottom here, this vertical marks. Those are the striations that are left on the bullet when it exits the barrel of a gun. And the question is, how do you compute a likelihood ratio? So if I have, let's say, these two images, and I want to know what's the probability that, let's say, X bar and Y bar are similar and how rare are they, then it gets a little interesting. So let me start with, so what I'll do now is I'll try to go over what we do in CSAFE on the surface. I'm not going to go into the weeds into anything, but I'll talk a little bit about shoe prints, bullets and handwriting. And so shoe prints is one of the areas we're working on. And by the way, for almost everything, we have built enormous databases because data are very scarce in this field. And if you go to our website, www.forensicstats.org, which is down here, and go to resources, you will get access to anything, all the data, all the algorithms, all the code, anything we have ever produced. And the databases are pretty well documented. And if you would like to play with any of our data, please do. In particular, for these shoe prints, we have a database of about 35,000 images, I believe it is, from a study we conducted at Iowa State. But in any event, let's suppose that you have these two images to compare. So Q here is the questioned image, the one you recover from the crime scene. And K might be the image with known provenance. So this may have been obtained from the bottom of the suspect's shoe. And the question is, let's suppose that I find a way, and I don't know how to do that yet, but let's suppose that I find a way to quantify the similarity between these two images. And so that degree of similarity is what I'm calling the evidence. And so the likelihood ratio here would be computed simply as the probability of observing the evidence, the degree of similarity, if the prosecution is right, same source, that's the S. And here I'm also conditioning on C, and this C here means class characteristics. So if this print, if the crime scene print looked like what it looks like here, and the print of the defendant's shoe had no circles on it, or was 3 sizes larger, or was a high heel, I don't know, something like that, was not an athletic shoe, then I would even need to do any comparison because what's called class characteristics are not in agreement. So class characteristics for shoes here is apparently the same size, apparently the same brand, apparently the same model, apparently the same degree of wear and tear. And sometimes it's not obvious, but in this particular case, it seems like those class characteristics would agree. And so we're conditioning on class characteristics agreeing. And the denominator is the probability of observing that evidence, even though class characteristics agree, but by chance alone, given that the defense is right. Now, to start working on this problem, we organized this. We conducted a study where we picked 2 different types of shoes. So this is a model of Adidas, and this is a model of Nike shoes. We bought 160 pairs of these shoes, and about 80 of each. And then we had volunteers, study participants, walk in the shoes for about 6 months. And what we did is every 4 weeks or so 4 times during the study, we asked these volunteers to come back to CSAFE, and we measured all kinds of things. So we imaged these shoes, using different types of instruments. We photographed the shoes. We tried to get a longitudinal set of images of each one of those shoes. This is the data that I'm telling you is in this big database that I just described. I'm going to show you results only for the Nike shoes today, the ones on the bottom there. And the first thing we did is we said, all right, actually, that's not the first thing we did. We did all kinds of things, but one of the last things we have been working on is, if you look at this, an image of the shoe, that image has about 10,000 pixels at the resolution we're getting them. So the first question is, can we reduce the dimensionality of the problem? And we've been recently focusing on this, on these attributes called serfs, speeded up robust features. So this is just a way of extracting information from this image. So what we do is we extract the 500 strongest serfs from each image and work with those instead of with the original pixels. So what we did too, so each shoe we imaged in replicates. So when the shoes came back to the lab, we obtained 4 replicate images of each shoe. So for each pair of shoes, we have 8 images at each measuring location from each instrument. So we have a lot of data. And so that allowed us to create pairs of mated and non-mated images. So images that we knew were obtained from the same shoe and images we knew were not obtained from the same shoe. And one way we also increased the amount of data was by flipping one of the shoes, so that the image of the right shoe can be compared to the image of the left shoe in a pair. So the next thing we came up with is methods to align those images using various approaches. One of them is we use the idea of a maximal click. So what we found was subsets of the serfs in one image and in the other image that were geometrically congruent, and allowed us to then use them to really come up with a fine alignment of the images. And then once we had those images overimposed, if you will, so one on top of the other, then we could start measuring things that would be associated to similarities. So for example, the size of the maximal click. You would think that if the two images are from the same shoe, the size of the click would be larger. The proportion of overlapping pixels, and so to define overlapping, we had a mesh, we allowed for a little wiggle in the distance between pixels, and then the median distance between the overlapping pixels. So for starters, only 3 features to see whether we could get anywhere. Oh, sorry, this is one of the instruments we use to obtain these images. It's called an Evero scanner, and it's what you step on it, you step on this area here, and then the scanner captures the contact of the shoe sole with the scanning surface to produce an image. It has to do with the pressure that is applied on each on the different areas of the outsole. All right, so in principle, we have 3 variables, x1, x2, x3, that we measure on a pair of images, not on each shoe, but on a pair of images. So again, in principle, we could think of computing the coming up with a probability model for the 3 metrics under the hypothesis that for the pairs that have a common source, and then do the same thing for the pairs that have a different source or from different shoes. And what I'm showing you there is some very rough or initial results just for illustration. So each of these, so what we have here is the values of x1, x2, and x3. The green for the different pairs, the green distribution here represents the value of x1 among non-matching pairs. This is the value of x2, and the orange is the value of x1 among matching pairs. So here's x1, x2, x3. x1 here is the log of the click size. x2 is the log of the distance between matching points, and x3 is the log of the proportion of matching pixels. And you can see this is kind of nice. So, so for example, the click size, like we had hypothesized, tends to be larger when you have matching pairs than when you have non-matching pairs, as you would expect. The distance tends to be larger among non-matching pairs than among matching pairs, but there is some overlap. So none of these three variables by themselves would give you a good classifier. What you would need to do is combine all three. So I have a student that's working in coming up with a principal probability approach to this question. But for the time being, okay, so in principle, given if I have a pair of shoes, a pair of images in a real case, let's say I'm a forensic examiner and I have a pair of shoes in a real case, and I compute this vector x tilde, let's say, for this particular pair of shoes, I could, in principle, compute a likelihood ratio if somebody tells me what this probability models are all about. And so one could also view this as a classification problem. And so one could, for example, take those three variables that I just showed you and combine them into some univariate similarity score. And one thing we have tried is come up with a random forest, call that G. And this is what you get. So there's, ignore the, let me see, ignore the red here. So the only thing I'm looking at is the green. The red is something else. And so it looks pretty darn good. So it looks like, at least for this particular set of data, the random forest is a very good classifier. In fact, the estimated error rate for this particular data set that we are playing with came up to be less than 3%, which is really very good. So woohoo about that. But and then maybe one can think of computing something that we might call a score-based likelihood ratio. So a score-based likelihood ratio would just be computed as, again, a ratio of probability models, conditional on same and different source. But now these probability models are univariate, so it's, that's kind of nice, and they are fitted to these functions of the original variables. Now this looks wonderful and easy, and it seems to work in many cases, but there's a few, there's a few things that one needs to be very worried about. One of them is that that the score-based likelihood ratio, you're losing a lot of information. What I'm trying to say is, when instead of using the original variables to compute this likelihood ratio, you're using some summary of the original variables, essentially what you're getting out of the whatever classifier it is that you're using on it. So everything that I showed you happened, was those great results we obtained when both images, what we call the crime scene image and the reference image, both of those were of reasonably high quality. What happens when one of those images is degraded? Well, as is much more realistic. So when the images are degraded, so how do we do? So things, of course, don't work so beautifully well. And so what we did is we took the same images we had, we deleted about half of those. No, sorry, we didn't take the same images. We took the same shoes we had. And to obtain great degraded images, what we did is we put 10 pieces of paper, 10 sheets of paper between the bottom of the shoe and the scanning surface, just to blur the edges of the image. And so this is what we would call a degraded image, and this is still the reference image that we obtained that we obtained from the study issues. And actually, the same kind of thing happens. So you still can observe a separate, quite a bit of difference between the same pair and different pair, same shoe, different shoe pairs of images. But the results are not as wonderful as they were. And in fact, what you see here is the ROC curves. Again, forget the red one. We're looking at the green one, the ROC curve. And now the estimated error rate for this particular example was something like 9%, I believe. And so we're still working on that. We're now working to create more realistic crime scene-like images. And stay tuned for more data on this. All right, firearms. What happens with firearms? Well, again, we have a very, very large database of firearms images, both bullets and cartridge cases. And so in this particular case, the question is, let's suppose you find a bullet at a crime scene, and then you get the suspect's gun, and you ask yourself, did the suspect's gun fire the bullets that I recovered? And here is a bullet, and if you guys are like me, you knew nothing about bullets until you heard this talk. And so here's ammunition on the top, and this ammunition has several parts. One of them is the tip here that I'm showing. I don't know if you can see my let me see. Okay, now you can see it. So the tip of this ammunition, this is what we call the bullet. And then the bottom here is called the cartridge case. And this is the bullet. This is what is ejected from the barrel of the gun when you fire the gun. You see these big marks here. Those are called grooves. And these grooves are made on purpose by design. So this, and they're made by design by the manufacturer of the gun. Every barrel has this what's called rifling, which are doesn't matter. So it's the design of the inside of the barrel that is put there so that the bullets in flight will rotate and be more stable. Anyway, so what firearms examiners focus on are the striations that are made, not this grooves, but rather the microscopic markings that are made by imperfections on the inside of the barrel. So the state of the art is, and I should have said that for shoes also, the state of the art is to essentially do visual comparisons. So you take a bullet and then you take a reference bullet, you put both under what's called a comparison microscope that allows you to rotate both samples until you think you have found the best alignment of those striations. And then examiners will reach categorical conclusions such as, I can identify this as the gun that fired this bullet, or I can exclude this as the gun that fired the bullet, or very commonly, I cannot tell one way or the other. So an inconclusive, what's called an inconclusive result. The problem with this, of course, is that this is extraordinarily subjective. So what may be enough matching striations to one examiner not necessarily means the same to a different examiner. And further, there's no rules that say you have to have this many striations to declare that these two things are similar enough. And so, not to mention the fact that identification here implies I am 100% certain, and statisticians kind of get the shivers when somebody says, I am 100% certain that this gun fired this bullet to the exclusion of all other guns in the country. So what we have proposed at CSAFE is to do this a little bit more scientifically. And so the same question that we had for the shoes, can we find a way to obtain measurements from the surface of these bullets and then use those measurements to come up with some sort of similarity value? So at CSAFE, what we did is we purchased several actually by now, high resolution instruments that allow us to get maps of the surface of these bullets, topological maps of the surface of these bullets. Essentially, what we're doing is we're measuring for if this is the X coordinate and this is the Y coordinate, we're just measuring at each point, we're measuring the depth of the striations. And what you end up with is just a flat XYZ file that may look like the one I have over here. And once you have this XYZ file, then there's all kinds of things you can do. So instead of looking at, so here's one area where people could perhaps improve what we're doing. So instead of looking at this entire surface of striations, we're looking for a crosscut a crosscut where we're looking at, we fix the Y and we look across the axis at the depths. And this crosscut is found by essentially a moving window that goes up and down and looks for the area where the cross correlation between the depth of the striations is maximized. So there's very little change as you go up and down on this surface. All right, so then once we have this crosscut, essentially we just do very simple statistics. If this is the image of the land that I showed you earlier, but now instead of looking at the surface of the bullet, we rotated it. And what dominates here is the curvature. This is one of what's called the beginning of one of the grooves. This is the beginning of the other groove. This is the area of interest. And so the first thing we do is come up with a single pixel representation of this, remove the grooves, the shoulders, I mean, and then what you end up with is something that looks like this. And you can see, again, still the curvature dominates, but you can see that this is not a smooth surface. There's deviations from that surface. So what we do is we fit a Lowe's curve, a non-parametric regression, a very simple one, which here is represented by the blue smooth curve, and simply extract the residuals. And these residuals are what we call the signature of a bullet land. And you can see, you can see here in this plot over here, that's a signature of a single land. Now, once you have this and this, by the way, is about 2 millimeters, this distance over here. And this is about what, 6 microns? And so we're talking small 6 microns? Yeah. And so we're talking small amounts of, these are tiny little things. And so when you have the signatures of 2 different bullet lands, you can align them like we did over here, again, using cross correlations. And once you have them aligned as best you can, then you can start measuring differences between these 2 things. So for the initial work we did, we were measuring 7 features here that were associated with the similarities or the differences. The features were things such as, the area of disagreement between these 2 sets of, between these 2 curves, and the distance between peaks and all kinds of different things like that. And none of the 7 features that we were measuring by themselves were good classifiers. But if you combine them, again, using a random forest, then suddenly you ended up with a pretty darn good classifier. And so what's the performance of this thing? Well, again, this is not the most up-to-date work, but we trained a random forest using a very non-representative set of bullets. In fact, there's one data set that everybody uses, which is 35 bullets shot from 10 consecutively manufactured barrels of a certain type of gun. So very non-representative. And we use that to train. And the question is, will the forest have good predictive ability, or will it be a good classifier if we try it out on other data sets? So we asked some police departments and crime labs to send us some samples, and we got several. So let me show you the results we got. The top here is some data we got from the Phoenix Police Department. And what they did is they sent us 3 test shots from each of 8 barrels and 1 question bullet. And then 10 question bullets, and they didn't tell us which barrel had fired those bullets. And so what we did is we tried out the random forest. And for example, we found that, so each column here represents one of those barrels. And from each one, we had test shots that we knew came from those barrels. So question bullet N, we compared to everything else, to every other, to all the reference bullets and to all the other question bullets. And orange here says that the random forest score was close to 1 when we compared it to the test shots from A9, but then everything else was gray, meaning all the other similarity scores were close to 0. Similarly with question bullet B, it looked like it came from CH and nothing else. We didn't find anything that would match the reference bullets from U10, and we didn't find anything that would match the last 3 question bullets, Q, Y, Z. We said these 3 were fired from some other guns, none of these. And it turns out these were all correct. The same with Houston Forensic Science Center. Again, they sent us a bunch of barrels, and again, everything was correct. So for example, U33 and U38, the question bullets both were fired from the same gun, KG, and then U27 was fired from KF, and we had nothing from KH and so on. I should say that the Houston Forensic Science Center not only sent these kits to us to try the algorithm, they also sent these kits to about 35 examiners. And the algorithm defeated the examiners handily. Not only the algorithm made no mistakes, and the examiners did make mistakes, the algorithm also had no inconclusives, and the examiners had about 35% of their responses were, I don't know. So, and this is what I just said. I'm running out of time, right?
Oh, so you're fine. Yeah.
I am? Okay. Yeah. So I don't know if I should go, well, very quickly, handwriting. Again, the question, you have these images, and the question is, how do you extract images from, features from the image of a handwriting sample? And we asked examiners, what do you guys look at? And the examiner said, well, we focus on the shape of the writing. So we look at the slant, we look at the connectedness of the writing, we look at the size of the loops. And so we thought, okay, let's see whether we can mimic that, but instead of doing it by eye, let's try to automate this and extract features and see whether we can do something more reproducible. So we did, we collected our own data set again, and again, this data are available. So at this moment, we have something like 200 or 300 writers, and each one has provided us with 9 samples of writing, more than that, sorry, 27 samples of writing collected at 3 different occasions. And the question is, can we identify, first of all, can we identify writers by the type of graphs they produce? And what do I mean with graphs? Well, we created a set of rules. We created this program called Handwriter. It's an R program that includes a set of rules to decompose handwriting into what we call graphs. And so, for example, if you take the word CSAFE, the program will separate the C, the S, then this A, it'll separate it into two pieces. So oftentimes the graphs correspond to letters, but not always, the F and the E. And once you have these graphs, then you can try to characterize the graphs using the nodes and the edges, and in particular using the shapes of the edges that connect the nodes. And so in the past, this is not a new idea. This has been done before in that others have proposed separating handwriting into graphical structures. But then what we came up with a different set of rules to do it. And we, in particular, came up with a much more flexible approach to analyze it. So what do you do with those graphs? And so if you look at a paragraph of writing, let's say just a normal paragraph, maybe 70 words or so, you will find that there's about 400 or 500 graphs, typically, let's say between 350 and 500 graphs in a paragraph. And each one of those graphs is a little different. So the question is, can you, again, reduce the dimension of the problem? And so what we try to do is we try to see whether we could take a document, extract the graphs, and then cluster the graphs into groups that are similar. And so, and then if we can do that, then we sort of characterize each one of these clusters by an exemplar, let's say, an exemplar graphs, and then use these clusters or cluster exemplars as a template. And let me explain to you what I mean by that. So what we did is we took a training data and we said, all right, let's see whether we fixed the number of clusters we were interested in obtaining into 40. And we did look at different sizes of different values for K. And of course, as you can imagine, this depends on the size of the document you're looking at. So there's much more to this than what I'm telling you. But for now, let me show you what happens when you have 40 clusters. The template here is obtained by, so here's what I mean by this. So the clustering here is an extension of the K-means clustering approach. And what we did is we used, so again, we're not the first ones to try to cluster graphs, but we did extend the clustering approach by including the shape of the edges into the distance metric that we compute for two graphs. And so here's what you are looking at is one of these templates that I'm talking about. So each one of these, so take the age cluster, for example. This includes graphs that look like U's or like incomplete A's or things like that. And the red is what we call the exemplar, which is the graph that is closest to all other graphs in the cluster. And then the gray around it is a measure of the variability of the graphs that ended up put in this particular cluster. This here is AB here, for example, is a compost pile in a sense. This is where things such as scratched words get allocated and so on. And so once we have these exemplars, then we can use those as a template. And so if I have a new sample of writing, what I can do is I can decompose it into graphs, and then I can see what the frequency of each type, and I can allocate those graphs to the best cluster, and then I can look at the frequency of graphs that each writer contributes to each one of these clusters. And that's what we use as data here. So the Y sub WD is it's a 40-dimensional vector of frequencies that we obtain for the Wth writer and the D document from that writer. So I'm going to, long story short, so we also use the slant of the graph. So that's one piece of data we have for each writer, each document. The other piece of data we extract is the slant. This is at the graph level. So we look we look at the angles with respect to the horizontal for each graph for each writer to represent the slant of the writing. And angles are kind of tricky because, of course, they live in a circle. And so when you model them, you have to be a little careful. And what we use to model these angles is called a wrapped Cauchy distribution, a distribution that lives on the unit circle. And you can see, for example, the red here is a fitted wrapped Cauchy for this particular writer's graphs in this particular cluster. This is for a different writer in the same cluster. And you can see there's quite a difference in terms of not only the mean, which in this case is 7 pi over 4, and in this case is in this direction, but also the concentration of the slants around that mean. So I don't have time to go over this in detail, but this is one example where we use, instead of using a machine learning, we use a standard statistical approach. So we fit a hierarchical model where we have these the vectors of frequencies for each person, and we just use a very simple multinomial likelihood and Dirichlet prior and a gamma hyper prior, and then we also model the angles again as a wrapped Cauchy, and at the end of the day so the wrapped Cauchy depends on two parameters, a location and a concentration parameter, and we allow those two to vary. So each writer and cluster combination has a mean and a concentration parameter. And then these are the hyperpriors. I'm happy to talk to anybody that's interested in this. The truth of the story is that this model fits beautifully well. So we end up with, we've tried it on many different samples of writing, including some obtained from Europe and from European databases. And the trick here, of course, is that the writer has to be, the true author of the question document has to be in the set that you're looking at. So this is a closed set approach. So if let's say somebody writes a threatening note in a high school and you look at some handwriting samples from the students in that high school, that would be a closed set of potential writers. We've extended this to the open set situation. Anybody could have been the writer, but of course, then we have to, again, rely on algorithms rather than just statistical models. But the accuracy is like in the high 90s, so it's pretty good. So I think I'm going to skip this because this is a different topic, which is why bother if examiners are pretty good. It turns out that examiners are not so good. And there's been several what's called black box studies recently that show that that if you look at reproducibility and repeatability among examiners, it's not very high. So there was a recent study that was done, as a matter of fact, in the Ames lab funded by the FBI, where they looked at firearms again. It's called the Ames 2 study. And it turns out that repeatability and reproducibility were, sorry, and I didn't tell what I mean. Reproducibility is the inter-examiner consistency, if you will. You show the same sample to two examiners, do they come up with the same response? And repeatability is you show the same examiner, the same sample at two different time points, do they come up with the same conclusion? And in this last Ames 2 study, the repeatability and reproducibility in firearms was no higher than about 70%, which is, and even if you aggregated data and did this and did the other thing, you could get as high as 80, 82%, but that's pretty bad when you think about it. And so all this stuff is really useful. So let me skip. All right. So let me just finish and say there's a lot of data, there's a lot of problems. We don't have all the best solutions. We're trying to come up with things that work and that at least improve the status quo. But there's any number of things that are kind of improvable, shall we say. And so here's the website for CSAFE. I'd be happy to talk with anybody that's interested. Let me give you a happy ending. So this is Keith Harward that I introduced at the beginning. As I said, he was exonerated about 6 years ago. And this guy is such a good guy. So he bought himself a camper, has a partner, and they've been running around the United States enjoying freedom like you would not believe. And so these are people that have been exonerated by the Innocence Project recently. There's white people, Black people, young people, old people, women, men. It is all over the place. And so this needs to stop. So thank you so much.
Oh, thank you, Alicia. Very interesting, very rich topic stuff. Any question from audience?
Thanks, Alicia. This is Shomik. Again, fascinating talk. Really appreciate it. So I was just curious about one thing that kind of when you were saying that you are trying to sort of emulate the situation with that shoe example, right? That you took sort of a bunch of papers and kind of emulate that situation, right? So so I'm wondering, like how do you ensure that that kind of noise is the noise going to be in the real situation, or like are there, like when you do the synthetic data generation? I mean, that's my kind of deeper question, that between synthetic and real. I mean, that's a very standard problem in machine learning these days, that we end up because we need a lot of data, we end up doing a lot of synthetic data generation and try to live with it. But then when to go from sim to real, there's a whole lot of transfer learning comes into play. And so, I just, your thoughts. I mean, I'm going to stop here.
No, I completely agree with you. And so what we're doing is we're actually, so we haven't generated, I mean, I don't know if by generated data, you're talking about like autoencoder type of generation.
Yeah, so yeah, I mean, generative models, we generated synthetic data, or in many cases, for example, I'm working on a project where you do sort of this gunman detection with cameras in school buildings and stuff. And we had to reside to a lot of video game data because that's where you can generate data at your will. And then we tried to see if we could transfer that model that was trained with video game data to real life gunmen, and we were successful to some extent. But I'm just curious that yeah.
So funny you should ask, and this is mostly out of ignorance. We have actually been trying to generate real data, not using models, but actually making prints.
Right.
And so the the question is whether the prints we're making are realistic enough in terms of do they look like real crime scene prints?
Right.
But we try, and but I have a student that is pushing for us to consider some of these generative models, and I suppose the best you can do is test it against real data. I'm not sure.
Yeah.
But we haven't used those yet.
Yeah, it's very difficult. I mean, I mean, because you are in real life, you are trying to sort of emulate that situation, right? So I was, are there principled approaches, or it's like, trying to be innovative and figure out how to, come up with similar prints, right?
Yeah.
Interesting.
So far, as I said, we've been using real data in the sense of
right.
not model generated.
Right, but to some extent, but artificially created, right? I mean,
yes. Yeah. I mean, there's always some of it yes and some of it no, right? So like the shoe print is an issue, but the handwriting is not
Right,
artificial, and the bullets are not artificial. These are
Sure.
this is what you. There's no good reason to think that these would be different from what we observe in real crimes.
Right. Yeah, at least it seemed like we are still far away from the TV shows that we see.
Yes. Well, I mean, yeah, the TV shows don't exist, right? This is so unrealistic.
Yeah. No, great.
So,
Thanks for the stuff. Yeah. Go ahead, Alicia.
when you talk about the similarity, I just try to understand that. So typically you compare with something you already know or you desire to be in some type.
Yes. So, yeah. So the way so what you want to do is you want to have some sort of automated algorithm that will allow that will classify a pair of images, let's say, of unknown provenance into same or different source. And so you have to train this algorithm. And so to do that, of course, you have to have labeled data if you're going to use a supervised learning.
Supervised, okay.
Yeah. And so this is all supervised. And so or at least most of what we do is supervised. So that's why we create this very large data sets with known ground truth, right?
Okay.
So that we can present these to the algorithm. And also we can use part of those data to test, to see how well this algorithm is working. The problem with real case data is that you never know ground truth.
Yeah,
that's at the end of the day, you don't know.
Yeah.
So that's the story. That's why these experimental data sets have to be created.
Correct. Okay. Thank you. Any other question?
Again, all this data are available to anybody that wants to go play with them. And the algorithms are all open source. And so anybody that can improve on what we're doing is more than welcome.
On your website, right? You show that.
Yes, go to resources and then you will get all kinds of stuff.
Okay, good. Okay, let's thank Alicia again. Thank you very much.
Thank you for the invitation.
Yeah, everyone has a nice spring break. Okay, bye-bye.
Bye-bye.